We're going to have Virgin Galactic joining Virgin Atlantic as a way to spend your tourism dollars, if you're stupidly rich.
But, you know, but the problem is, I think that's all a scam. But, you know, but the problem is, I think that's all a scam. Scam. I really do. I think I just got asked about this. The point is that it's exponentially, look, to go in Earth or near Earth orbit, you know, to go the distance between New York and Washington above the Earth, yeah, maybe private industry can do it, but it's just the laws of physics say it's just exponentially more expensive and exponentially more difficult to actually explore somewhere interesting.
Yeah.
And and therefore I don't think it's ever going to be. I don't think private industry is ever.
So let's have a look at the rocket engine nozzle. And Wikipedia defines a rocket engine nozzle as a propelling nozzle used in a rocket engine to expand and accelerate the combustion gases produced by burning propellants so that the exhaust gases exit the nozzle at hypersonic velocities. Let's scroll down to atmospheric use. The optimal size of a rocket engine nozzle to be used within the atmosphere is achieved when the exit pressure equals ambient atmospheric pressure, which decreases with altitude. So atmospheric pressure is air pressure. So right there in that first sentence, they are saying that rocket nozzle design and efficiency of such is dependent upon the ambient atmospheric pressure, the air pressure, which decreases with altitude. So if a rocket is travelling from the Earth to orbit, a simple nozzle design is only optimal at one altitude, losing efficiency and wasting fuel at other altitudes. So what they're saying there is, in an ideal world, they would have a nozzle that changes its shape and its dynamics as altitude increases, because there's only, if it's a fixed shape, there's only one altitude at which it's at its optimal. So let's go down to the vacuum use. Now, the whole premise of this video is that I don't think rockets can work in a vacuum. So the first sentence that it says here, I think, is applicable if you remove the word vacuum, because it describes high altitude. So let's read it. For nozzles that are used in very high altitude, it is impossible to match ambient pressure. Rather, larger area ratio nozzles are usually more efficient. So right there they're saying that at high altitude, the ambient air pressure is so negligible that they need to put much larger ratio nozzles on to account for the loss in air pressure. So again, air pressure is small at high altitude, therefore larger area ratio nozzles are more efficient. If you take this to its logical conclusion and traverse into space where air pressure is zero or very near to zero, how big or what area ratio nozzle are you going to need then? Would this be infinite? Do you see what I'm saying?
But in spite of the mathematical evidence, any further attempts to restore belief in the flat Earth seem doomed by one of the supposed great moments in modern scientific achievement. At last, after thousands of years of uncertainty, man was able to get far enough away from the Earth to have a good look at it in all its resplendent beauty.
So, rockets working in space. Never bought it myself. I propose that you need something to push against in order for propulsion. And since there's no atmosphere, it's a vacuum in space, there is nothing to push against. So I was going to start by showing this video of Apollo 11 launching to go to the moon back in 1969. This is the one with Neil Armstrong and Buzz Aldrin. And you'll notice in this video that the rocket starts out ascending vertically, but as time goes on, it starts leveling out and flattening. And the reason they say that this happens is so that they can take advantage of the Earth's gravitational force, which gives them a slingshot effect to propel them into space, giving them a higher velocity to do so. Now, we are told that the reason we don't experience the force of us spinning at 1,000 miles an hour at the equator is because we have this atmosphere that's kind of in sync with the rotational spin of the Earth. Therefore we don't feel anything. And since gravity is a constant, I don't buy the idea that they're using the gravitational force of the Earth to slingshot themselves anywhere. You can see now the rocket's levelling off, and you will not find a single video anywhere of any rocket ascending vertically, much less actually going into space, you know, leaving our atmosphere. None. You'll find none anywhere. You'll see that the altitude that's been superimposed onto the screen there at 25 kilometers roughly now, 26, 27, is increasing so quickly, even though the rocket is coming up to being completely horizontal. So it's horizontal now, and it's increasing in altitude: 40 kilometers, 41 kilometers, 42 kilometers, 43 kilometers. How can that be happening? So let's look at the textbook explanation of how rockets work, more specifically how they work in space. So I've got nothing against this guy. He obviously reads textbooks and absorbs the information within them, but like a lot of these people, they can't actually test these things for themselves. They rely on what they read and just accept it. So this guy is called, his name is Robert J. Dolby. He's a member of the Royal Astronomical Society, and he's also the curator of the Wernher von Braun Rocket Academy. So let's listen to what he has to say on the subject.
In this brief video, we're going to answer the question, what makes a rocket fly? Now that question refers to all rockets and all missiles. They are all the same in this regard, and the short answer is Newton's third law, which states, for every action there is an equal and opposite reaction. Maybe you're thinking that's not helping your understanding very much at this stage and you want a little bit more detail. Okay, thinking caps on, pens and paper at the ready. I'm going to be asking questions later. Or do you feel that algebra and quadratic equations really aren't going to help you that much either? Okay, you're in good company. You'll find that there hasn't been a missile man or woman in the history of rocketry that has really understood why a rocket flies by looking at those kind of calculations and understanding the rocket equation. We actually get our understanding of how the rocket flies from a very simple understanding. It's related to that Newton's third law, and it's the reaction principle. Now the good news is the reaction principle is actually something that's easy to understand, because it turns out you're already very familiar with it. You might not be able to identify it and know what it is, but you're already very familiar with this idea of the reaction principle. Now, some of the times that you've thought about what makes a rocket fly, you may have got, if you're not already sure about how it works, you may have got a little bit confused by what you've seen. You may have seen, everyone has seen lots and lots of images of rockets taking off, and it's easy to think that there's a secondary action going on with the rocket pressing on the ground, and after it starts flying you might start thinking that the rocket is somehow pushing on the air, and that's how it's moving. So it's not always absolutely 100% clear as human beings when we see something that we can actually see cause and effect. All we can ever really see is one type of event followed by another type of event, and we tend to actually then add the causal action based on what we've actually seen and other things that we're familiar with. So in any explanation, I'm going to go from things that you're already familiar with to something that maybe you're slightly less familiar with. So the reaction principle, it's something you've encountered in very simple terms. I think everyone's familiar with this example of the reaction principle. Here's an example everyone's seen, the lawn sprinkler. It's the reaction principle obeying Newton's third that makes it rotate. And you must have felt the shower head moving in your hand as you turn the tap on and off like this. Again, it's the rocket's reaction principle in action. The rocket motor, the jet from the rocket motor, isn't pushing on something. It's not pushing on the ground. It's not pushing on the air. It is the very expulsion of the jet from the rocket nozzle of the rocket motor that causes an instantaneous and simultaneous motion of the rocket in the opposite direction. Remember, this is Newton's third law in play, which is that every action has an equal and opposite reaction. So the action in this particular example is the jet stream from the rocket nozzle, and the reaction is the movement of the rocket motor, and thereby the rocket body as well, in the opposite direction. And the beauty of that is, and the true power of the rocket, is that it can do this in the atmosphere of the Earth, it can do it underwater, believe it or not, and it can also do it in the vacuum of space. And it's specifically because it doesn't need to push on anything to be able to make its transit. And that's what makes the rocket fly.
Okay, let's have a look at the scientific method. This is one that I found on Wikipedia. It's as good as any, I guess. So at the top there, make observations. Well, I see rockets flying in Earth's atmosphere. I don't see rockets flying in space. Think of interesting questions. Do rockets work in space? Formulate hypotheses. What are general causes of the phenomenon I am wondering about? Well, perhaps rockets don't actually work in space, and that's why I don't experience the phenomenon of seeing them. Develop testable predictions. If my hypothesis is correct, then I expect A, B or C. Well, this is where we mere layfolk are most vulnerable, as it's virtually impossible for us to test. We have to rely on the big budget space agencies like NASA. The best we can do is observe and test what happens here on Earth, and to hypothesize about what would happen in space. So my hypothesis is that Newton's third law of motion needs a caveat. This being that only when a fulcrum is present, this being a mass for the action to act upon, will Newton's third law apply. If such a mass is not present, despite the presence of an action, then a reactionary force will not be observed. So gather test data. Relevant data can come from the literature, new observations or formal experiments. Thorough testing requires replication to verify results. So I'm going to show you my experiment in a few minutes. But before I do that, I just want to wrap up this scientific method, and we have to develop general theories. And the theories must be consistent with all other relevant data. So if you go to NASA's website and go to the rocket principles section, it says a rocket in its simplest form is a chamber enclosing a gas under pressure. A small opening at one end of the chamber allows the gas to escape, and in doing so provides a thrust that propels the rocket in the opposite direction. A good example of this is a balloon. Air inside a balloon is compressed by the balloon's rubber walls. The air pushes back so that the inward and outward pressing forces are balanced. When the nozzle is released, air escapes through it and the balloon is propelled in the opposite direction. So going back to NASA's rocket principle page, if you scroll down, it says that one of the most commonly asked questions about rockets is how can they work in space when there's no air for them to push against? And this is my exact question. The answer to this question comes from the third law. Earlier on in the page it describes a skateboarder pushing away a skateboard with his foot, and describes the effect and the fact that the skateboard will move much further than what the pusher moves, and explains Newton's third law this way. So it says, imagine the skateboard again. On the ground, the only part air plays in the motions of the rider and the skateboard is to slow them down. Moving through the air causes friction. or as scientists call it, drag. The surrounding air impedes the action-reaction. So the only factor that they're saying that air has on the rocket is drag on the actual body of the rocket and friction, which causes it to slow down and not be as efficient. So they're saying, as a result, rockets actually work better in space than they do in air, because obviously there's no air to cause friction. As the exhaust gas leaves the rocket engine, it must push away the surrounding air. This uses up some of the energy of the rocket. In space, the exhaust gases can escape freely. So what it's saying is that in space, the expanding gas from the nozzle of the rocket doesn't have anything to push away on. It doesn't have to push away any air, thereby it's more efficient and actually works better. However, the whole premise that it doesn't need air in the first place is my whole problem with this law. As stated earlier, I believe it needs a fulcrum, or a point of leverage, for the rocket to work. So in the balloon experiment that I've just done, the reactionary force is in the opposite direction of the nozzle of the balloon. So the nozzle is at one end, at the rear, and the movement that we experienced in my first test was in the complete opposite direction. So that part of Newton's third law works. There is an equal and opposite reaction. However, it still needs that leverage in order for it to work. I would give the analogy of trying to do a pull-up. If you pull yourself up on a bar, you can lift your own body weight. The bar, in this case, is the point of leverage, the fulcrum. If you try to lift yourself up just by merely standing on the ground, and just grab yourself by the waist and try and lift yourself up, you can't do it. This is because there is no leverage point. You're pushing against yourself. This, in my mind, is a perfect analogy of what we just experienced with my balloon experiment. The balloon needed a fulcrum, something to push against, in order to make it move. Now you may have noticed that in a couple of the tests, the balloon actually rotated around the string, sort of radially, and this only further gives credence to my caveated addition to Newton's third law, because what was actually happening is the air escaping from the balloon was disrupted by the paper, and it was disrupted such that it was pushing air unequally from either side of the paper, because I haven't put the masking tape and the paper on exactly square, exactly perpendicular and centrally to the balloon nozzle. It created an imbalance, and it was pushing the air out of one side and caused it to rotate around the string, not in the direction that Newton's third law states that it should, which is the opposite direction to which the air is escaping. So let's wrap up the scientific method and see if there's any other theories out there that are consistent with our data that we've collected. So let's have a look at the rocket engine nozzle. And Wikipedia defines a rocket engine nozzle as a propelling nozzle used in a rocket engine to expand and accelerate the combustion gases produced by burning propellants so that the exhaust gases exit the nozzle at hypersonic velocities. Let's scroll down to atmospheric use. The optimal size of a rocket engine nozzle to be used within the atmosphere is achieved when the exit pressure equals ambient atmospheric pressure, which decreases with altitude. So atmospheric pressure is air pressure. So right there in that first sentence, they are saying that rocket nozzle design and efficiency of such is dependent upon the ambient atmospheric pressure, the air pressure, which decreases with altitude. So for rockets travelling from the Earth to orbit, a simple nozzle design is only optimal at one altitude, losing efficiency and wasting fuel at other altitudes. So what they're saying there is, in an ideal world, they would have a nozzle that changes its shape and its dynamics as altitude increases, because there's only, if it's a fixed shape, there's only one altitude at which it's at its optimal. So let's go down to the vacuum use. Now, the whole premise of this video is that I don't think rockets can work in a vacuum. So the first sentence that it says here, I think, is applicable if you remove the word vacuum, because it describes high altitude. So let's read it. For nozzles that are used in very high altitude, it is impossible to match ambient pressure. Rather, larger area ratio nozzles are usually more efficient. So right there they're saying that at high altitude the ambient air pressure is so negligible that they need to put much larger ratio nozzles on to account for the loss in air pressure. So again, air pressure is small at high altitude, therefore larger area ratio nozzles are more efficient. If you take this to its logical conclusion and traverse into space where air pressure is zero or very near to zero, how big or what area ratio nozzle are you going to need then? Would this be infinite? Do you see what I'm saying? So if we go back to look at what NASA claim on their Rocket Principles webpage, they claim on the ground the only, and I must stress that word that they use, the only part air plays in the motions of the rider and the skateboard, or in our case the rocket, is to slow them down. Moving through the air causes friction, or as scientists call it, drag. So they are claiming that the only part air plays with rockets on the ground in the Earth's atmosphere is the drag effect that's caused by friction on the body of the rocket itself. Nothing to do with the propellant dynamics. So they are claiming the exact opposite of what Wikipedia are telling us, because they're telling us that there's only one altitude at which a particular shape nozzle or size nozzle is optimal, and that they have to actually increase the nozzle ratio as altitude increases.
Our mission as the Civilian Space Exploration Team is to be the first civilian team in history to launch a rocket that reaches space.
All systems are go for launch. T-minus 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1.
Second burn. Uh-oh. Uh-oh. Uh-oh.
He's in a roll, it appears, at this point. Does not appear. All right, we are in the box and ready to go. 10 seconds to release. Cross your fingers and say a prayer.
Okay, here we go, guys. It's real tough to see. Okay, tally
There
ho
he
the
goes.
smoke. There he is, guys. He's on the climb.
He's riding the fingers of flame.
Look, you can
into
see the
eastern
flame.
sky.
You can see the flame from here, Mike, or Jim.
Our webcast viewers are enjoying unprecedented camera coverage from the ground here. A radar-locked camera from Edwards Air Force Base tracking Spaceship One as it streaks through the sky to punch through the atmosphere and reach suborbital flight. "35 seconds, 135,000 feet into the flight.
Looking for an 87.
Appear to be a scripted maneuver.
Shut down. Come on, Mike.
We have shut down main engines to Spaceship One.
Still in the climb.
250,000 feet, still in the climb.
5 knots indicated, so feathers coming.
These are the tense moments, folks. Communications with Air Show Center here have been cut off, and we are waiting to hear from them that Mike Melville is okay. All systems are nominal.
Wow, look
There's
at
your
that.
downlink camera
Look
from
at that,
aboard
folks.
Spaceship One, looking down at the Earth.
330, they made it, Jim.
330,000 feet.
They made it. Yes.
$330,000, that would put them over the top.
Yep.
328,000 feet needed to achieve the required altitude of 62 miles, 100 kilometers.
Have Virgin Galactic joining Virgin Atlantic as a way to spend your tourism dollars if you're stupidly rich.
But, but the problem is, I think that's all a scam. But, but the problem is, I think that's all a scam. Scam. I really do. I think I just got asked about this. The point is that it's exponentially, look, to go in Earth or near Earth orbit, to go the distance between New York and Washington above the Earth, yeah, maybe maybe private industry can do it. But it's just the laws of physics say it's just exponentially more expensive and exponentially more difficult to actually explore somewhere interesting.
Yeah.
And therefore, I don't think it's ever going to be. I don't think private industry is ever.
Of shock diamonds in its wake. At 2,200 miles per hour, the aircraft becomes superheated from the friction created as the air rushes by.
And indicating Mach 3.0 at this time.
When you go Mach 3, the amount of heat that the whole airframe, everything experiences all this heat, and nothing that they have at the store works. You know, there's no paint, no rubber, nothing. You know, metals, plastics, all this stuff is useless. And they just had to go through so many contortions to make every single part of the plane tolerant of these extreme temperatures.
Temperature affects everything on this airplane. The average person probably is not cognizant of that fact, but the faster you go, the harder things get.
One of the puzzles of extreme heat was never really solved.
Sealants for the fuel tanks. They never came up with a polymer that would seal the joints in the skin panels that hold the fuel in, so the blackbirds sit on the ground and weep. That seems silly. You can look, oh, these stupid guys back in the 60s didn't know what they were doing. There's still no plastic, you know, that can get to 700F and not turn into burnt hot dog oxide.
At an altitude of 30,000 feet, the X-1A is air-launched from the B-29. The plane begins its steep climb with rocket engines blasting it upward at supersonic speed. 4 minutes later, the X-1A was at 90,000 feet, a distance of almost 18 miles into the heavens. Major Murray has described his feeling upon reaching the tremendous altitude as one of incredible loneliness, especially when the skies darkened around him and the Earth's curvature became clearly visible. Yes, this is the X-1A. Its records of 1,650 miles per hour and 90,000 feet in altitude are more achievements in aviation science, and they will bring valuable data to be used in the tactical aircraft and guided missiles of the future for the nation's defense.
Quiet dawn to a big day, December 14th. For several months, the Air Force had been proud owner of the world's altitude record, set in May of 1958 by an F-104. It had quite a run for a modern record, but first a Russian T-431 and soon afterward a Navy F-4H sent it tumbling. The new Navy mark, 98,560 feet. The Air Force wanted to get it back, but odds were against it. No modern jet has ever been able to recapture its own record. The earthbound people keep watch. There he is, angling down after his swift high leap. He has been where no other man ever has. He's hacked it, beat the Russians by 1.5 miles, and the Navy by almost a mile. The new record, 103,395.5 feet. He's hacked it, beat the Russians by 1.5 miles, and the Navy by almost a mile. The new record, 103,395.5 feet.
Hi guys, this is Dr. Aeronautics. Here's a quick video of our great trip to 100,000 feet. This is actually a playback of me attempting to set the world altitude record. So basically I realized that reaching 100,000 feet is going to be a lot harder than I originally thought. So I figured the only way that we would be able to see this on YouTube without me recording 1,000,000 times over and dying of exhaustion was to record each one, and then when we got the successful one, go ahead and do that. So I've been trying for a long time, and today on my 4th attempt, I set a record above 100,000 feet. And I was so excited when it happened that I started screaming yes like crazy. So I'm actually going to mute the microphone when we get there. But I'll just basically explain what I did as I try and find it. So let me go ahead and find the start of the zoom. Okay, so this is right before the zoom. First of all, we had an engine modification by a little bit to allow us to travel up to Mach 2.2 in spite of us not being okay usually at that temperature. We're also starting at 46,400 feet, which is the working number that I decided was good. And here is my countdown. 3, 2, 1, zoom.
On the move, over. I'm descending the ladder. Tranquility, over. On the bottom rung of the ladder. Just one more step and I'm... Tranquility.
Gentlemen, will you please take your seats so we can begin today's conference? I take a great deal of pleasure in presenting to you today as our guest speaker, Dr. Werner von Braun. Dr. Braun.
Gentlemen, the conquest of outer space is the greatest technological challenge of the age in which we live. The first decisive step in the conquest of space will be the placing of an object into an orbit wherein it will indefinitely circle the Earth. It takes a speed of approximately 18,000 miles per hour to accomplish this. And this is approximately 3 times the greatest speed ever attained by rockets today. How can we reach such a speed? First of all, of course, one could think of improving propellants used in present-day rockets. Secondly, we could shave some weights of our designs. But with both these methods, it does not appear possible to gain more than approximately 40 or 50% of the speeds that rockets reach today. A fundamental step ahead in increasing the speed will be the application of the multi-stage principle. Let us take a look at our first slide. Through the ballistic trajectory, you have weightlessness. Such a long 3-minute weightless ballistic parabola is shown in the upper part of this picture. The next slide shows what happens inside an airplane flown through such a ballistic trajectory. you see a little matchbox floating in the left upper corner of the canopy. This matchbox was released by the passenger in this flight and was photographed by him to show that the matchbox is actually floating freely in the canopy, and it floated there for approximately 40 seconds. In fact, pilots who have repeatedly flown through such ballistic trajectories even use such free-floating objects to make sure that they are right under the weightless condition. If they apply a positive or a negative lift, the matchbox will come up and down. If they have too little or too much thrust, so that they either under or overcompensate the aerodynamic drag, the matchbox will move fore or aft.